In today's lesson, we want to talk about the vector and parametric equations of planes. We had discussed that the vector equation of a line consists of a point and a direction vector. To find the vector equation of a plane, the only thing we have to do is add a second direction vector. This second direction vector cannot be collinear to our first direction vector. So let's take a look at an example here. So to create a plane here, what we're going to do is we're going to start off with a point. Let's start with the point 0, 0, 5, and we're going to add two direction vectors to this point. One direction vector we'll label with a V, and you can see here it's going off in this direction. Then we're going to choose another direction vector, non-collinear vector, label that with a W. Again, both these vectors start at our point here, and we're going off in different directions, and again, these direction vectors have to be non-collinear. Now, what a plane is a plane is a collection of all possible points that are just linear combinations of these vectors, or direction vectors, in this case V and W, which start at our point, in this case 0, 0, 5. So how do you express this algebraically? Well, our vector equation would look like this. Notice here, if you look at the bottom here, we have our point 0, 0, 5 plus some multiple of our first direction vector plus some multiple of our second direction vector. Let's take a look at some points that exist on this plane. One point that exists on this plane is the point 3, -1, and 3. How we got that was we take our point U, which is in this case 0, 0, 5, plus V plus W, and that'll give us a point on the plane. Likewise, we could take another linear combination of these vectors. In this case, we have our point U again, 0, 0, 5, plus double our direction vector V minus our direction vector W, and that'll generate another point on the plane. Taking all combinations of S and T, we will generate the following plane. And you'll notice here that our 2 points that we've described are on the plane, plus there's infinitely many points on this plane, all of which consist of your point 0, 0, 5, plus linear combinations of your direction vectors. Let's take a look at some examples working with equations of planes for vector and parametric form. In our first equation here, we want to find the vector and parametric equation of a plane that passes through the points A, B, and C. Drawing a quick plane here, I just plotted points A, B, and C. I'm not looking to make these oriented properly or anything like that, just a visual that we have a plane and we have 3 points on it. And you can denote a plane with the symbol pi, by the way. What we need to determine the plane, as we saw in the previous description, is a point and 2 direction vectors. Well, we have 3 points here, but what I can do here is I can create my own direction vectors. I can create a direction vector AB, and I can also create a direction vector AC. AB will be our direction vector 0, -2, -8. AC will be our second direction vector 5, -2, -7. So now that we have 2 direction vectors, we just need a point. We can pick any one of these points here. I'll pick point A. So let's create our vector equation of our line. The vector equation of the line with V equals our point. And again, in this case here, I've chosen point A, so it'll be -1, 3, and 8, plus any scalar multiple of our first direction vector, 0, -2, -8, plus any scalar multiple of our second direction vector, 5, -2, and -7. So therefore, one representation of the plane will be the vector -1, 3, 8, plus S times 0, -2, -8, plus T times 5, -2, -7. Now notice here, one thing you could do is you can scale down your direction vectors. This direction vector here is 0, -2, and -8. I could pick any direction vector that is a scalar multiple, i.e. collinear to this direction vector, and that would be fine as well. So if I divided across by -1/2, we would have 0, 1, and 4, and that just makes it easier with future problems to work with that direction vector as the numbers are smaller and non-negative. If I want to express this in parametric form will be x equals -1 plus 0s plus 5t will be -1 plus 5t. Y will equal 3 plus s minus 2t. And lastly, z will equal 8 plus 4s minus 7t. And again here, s and t are any real number. So notice here we have our vector equation of our plane and our parametric equation of our plane. Also make further notice that this equation is not unique. I could derive another equation for this plane had I chosen different direction vectors. I could have chose the direction vectors b to c and a to b, and I could have chose a different point, let's say b or c. No matter what you choose, these equations of the planes will be equivalent. All right, so in this next example here, what I want to do is I want to look at the plane that we created in the previous example. So using this plane here, we want to ask, is the point P on the plane? How about the point Q? So what does it mean for a point to be on a plane? Well, for a point to be on a plane, it must mean the following. For instance, if point P is on the plane, therefore 14, 1, and 3 must equal our point, plus there must be some s value such that when multiplied by our first direction vector plus some t value, which then when multiplied by our second direction vector and summing all of this up must equal 14, 1, and 3. So this will generate some equations for us. Notice, first equation says 14 must equal negative 1 plus 0s plus 5t. Our second equation says that 1 has to equal 3 plus s minus 2t. And our third equation says that 3 must equal 8 plus 4s minus 7t. For equation 1, we get 14 equals negative 1 plus 5t. Solving for t here, we get t equals 3. Substituting that into equation 2 and solving for s, we get s is 4. So therefore, the parameters of s being 4 and t being 3 are the parameters we need so that 14, 1, and 3 is on the plane. However, we must check to see whether these two parameters satisfy our third equation. Checking this in our third equation, we see that the left-hand side will equal the right-hand side, and therefore 3 equals 3, and therefore this point is on the plane. Let's take a look at point Q. So checking point Q on this plane here, generating the exact same equation, notice the first two coordinates of P and Q are the same, so therefore it's going to yield the exact same equation, and therefore the exact same S and T parameters that are required. Subbing this into my third equation, we get that 5 is not equal to negative 9, and therefore point Q is not on the plane. In the following example, we want to find the parametric equation of a plane that is parallel to the xy plane and contains the point 135. Let's take a look at a visual to help us with this question. So they want us to create a plane that's parallel to the xy axis. What I've done here is I've drawn ourselves the xy plane here. You can see here the xy plane is generated by two vectors. One direction vector is 1, 0, 0. The other direction vector is 0, 1, 0, or any multiple of those. Let's take a look at that. So I've drawn here our two direction vectors. This is actually direction vector 5, 0, 0 and 0, 5, 0. But again, any scalar multiple of those two direction vectors plus the point, and the point in this case is the origin, that'll generate your xy plane. Now we're going to create a plane that's parallel to this plane and passes through the point 1, 3, and 5. So therefore what we're going to do here is we're going to use our point A as our starting value, and then we're going to add scalar multiples of our direction vector starting at point A in one direction, and then scalar multiples of our second direction vector going in the other direction, and this will generate our plane. And you'll notice here now we have our plane here in red. This plane is parallel to the xy plane, and notice the direction vectors that generate the plane in red is exactly the same as the direction vectors that generate our xy plane. So therefore, the only thing we have to do to create our plane, express our plane, is we use our point, in this case our point A, which is given to us above, plus our scalar multiples of any of our direction vectors 1, 0, 0, or 0, 1, 0, or in this case here 5, 0, 0, or 0, 5, 0. Let's take a look at putting this together to finish the question. Notice here the vector equation of the plane is just going to be our point. In this case, this is our point A, plus any multiple of our one direction vector, plus any multiple of our second direction vector. The parametric equation of this plane will be x equals 1 plus s, y equals 3 plus t, and z equals 5, where s and t are any real numbers. That concludes today's lesson on vector and parametric equations of planes. Thank you.